Okay, thanks, Ben. As mentioned, my name is Tiago Lam. I'm currently working for Intel. I'm based in Ireland, and as part of my main activities, I work on feature development around DPDK acceleration in OVS. And so today for the session, we're going to be talking about one of those features, and that is TSO. So for the agenda of this session, we're going to start with the first things first. So we're going to start by defining what is TSO. I'm aware that many of you may already know what TSO is already, so we're not going to spend too much time on this, just to make sure that we're all aligned. Then we will proceed and clarify why do we think there's a need to bring TSO into user space, since it already exists in the kernel. What is our motivation here? And we'll also define here our use cases of interest. Then we'll quickly move on into the gist of this presentation, which is explaining how we have enabled TSO in OvS-DPDK, and in specific, how we had to add support for a prerequisite, which is the multi-segment MBUFs. Then we'll show some performance results that we've been getting during our tests, and speak about some of the considerations that we have found while enabling this piece of work, which has some complexity attached to it. And finally, we also give you a status of the work presented here. And so, what is TSO? So TSO stands for TCP Segmentation Offload, and it's basically the process of offloading the segmenting of larger chunks of data into smaller segments into the NIC hardware. And so the NIC hardware really becomes responsible for the operations that we see here in the diagram. So not only segmenting those larger chunks of data into smaller segments, but also calculating then the checksums on those segments. And so this frees the CPU to do other more useful work. You might have also heard of GSO, and that is the same concept as TSO. However, it's implemented in software. And so it's, as such, it's usually a bit more flexible than TSO, so it's implemented in software, but it's usually also less performant than TSO. Now, although both of these concepts are already in the kernel, they're not in user space. And this creates a big gap between OvS-DPDK and OvS Kernel, especially around virtualization use cases or use cases that have intensive TCP workloads on them. Back in 2016, we had a colleague at Intel giving a presentation here at OvS-Con, where he presented the work that he was doing at the time between Intel, in a partnership between Intel and a telecom provider. And his presentation was around how to improve the TCP workloads in OvS-DPDK overall. However, the use cases that he defined at the time are still the use cases that we're interested in. And so we can split those use cases between two main categories. So we have the intra-host use case represented here by the orange path. And that's basically VMs communicating between each other within the same host. And then we have the inter-host use case, which is VMs communicating between each other, but across hosts, and which is represented here by the yellow path. Since that presentation back in 2016, we've had a few more requests, either from direct partners or indirectly, in order to support TSO in OvS-DPDK. And it's something that comes up even on the OVS Discuss mailing list quite occasionally. Either people asking if OvS-DPDK supports TSO, or people just pointing out the performance gap between OvS-DPDK and the OvS kernel. Now, if we try to zoom in into our previous diagram, and we try to represent all of the components at play there, we can fairly easily see where the performance bottlenecks are coming from. And so if a VM is trying to send a large chunk of data, what will happen is that the TCP IP stack running on the kernel within that VM is going to segment that larger chunk of data into smaller segments according to the MTU configured on the virtual NIC of that VM. And later on, it will also perform the checksum calculations on those segments. And these operations are being done in software. So more specifically, they're being performed by the virtual CPU assigned to this VM. However, if that data was originally meant to be sent to a VM running within the same host, which is represented here by the orange path, then segmenting the data according to the MTU of the network, or even performing the checksum calculations on those segments, is of no use at all, since the data won't be actually bit transmitted outside of the host. Instead, on the other hand, if the data was originally meant to be sent to a VM running on another host, then since the data is actually leaving the host, then segmentation and checksum calculations will need to be performed. But it doesn't necessarily mean that those operations need to be done within the VM. And they could instead, as it happens with TSO, be done by the egress NIC, and only if the data is actually leaving the host. And so from the previous slides, we can really take two conclusions about the cost of running without TSO. And that is that we should expect higher CPU loads, and this is because both of those operations, the segmenting of data and the checksum calculations, are being done in software instead of hardware. And then we should also expect lower overall throughputs. And this is because instead of transferring larger chunks of data, as it happens on the intra-host use case where there's no need to segment the data, and we could be sending data in the packet. We could be sending kind of large chunks of data of more than 64 kbytes. We're instead segmenting those into smaller segments. And so we should expect lower throughputs as well. And so in order to kind of close the gap around these use cases around virtualization that we have just discussed, and that have a strong TCP requirement around them and are usually seen around telco environments, we set out to bring TSCA into OvS-DPDK. However, in order to enable TSO, in our use cases, we had to first add support for a prerequisite, and that is the multi-segment MBUFs. And so you can see an MBUF in DPDK as basically the DP packet struct in OVS, or even the skbuf struct in the kernel. So it's basically the structure that holds the packet data, and it also has a few other metadata associated with it. So in OVS master, currently OvS-DPDK doesn't make use of multi-segment MBUFs at all. So it only uses what we can call the simple single MBUFs. And so what happens in the typical deployment is that OvS-DPDK allocates the maximum, it allocates to each MBUF the maximum size that it expects for each packet on the network. And that is based on the MTU configured, plus a few extra bytes for some optional VLAN headers. However, this doesn't bring too much flexibility, since if a smaller packet is coming on the wire, then we're going to be wasting space, since we have larger MBUFs allocated. And in the worst case scenario, if a larger packet is coming on the wire, then we're going to have to drop that packet, since we have no MBUF actually capable of holding that packet. Now, this isn't too much of a problem on the typical deployment scenario, since in the typical deployment scenario, you have physical interfaces attached that have an MTU configured, and that MTU must be respected. However, if we're planning to enable TSO within the VM in order to get larger packets from the VM into OvS-DPDK, then we don't necessarily know how large those packets will be. And so in order to circumvent that problem, we brought in the multi-segment MBUFs. And so the multi-segment MBUFs is basically a chain of those single MBUFs, single segment MBUFs that are chained together using the next pointer in the MBUF struct. And so that's how you can traverse the chain, as we can see here in the diagram. And in this case, what we can see, what happens is that this gives a better flexibility to our deployment. Sorry, I went one ahead. What happens is that this gives a better flexibility to our deployment, since if we now have a smaller packet coming on the wire, then we can always drop an MBUF from the chain and use that MBUF for something else and not be wasting that space. And if we have a larger packet instead coming on the wire, then we can always attach another MBUF to the chain in order to be able to hold that extra data. However, this doesn't come without drawbacks either. And the main drawback around the multi-segment MBUFs is that now, instead of having the data being represented in memory contiguously by a single MBUF, we now have the data spread across a chain of MBUFs. And so this means that we had to rework some pieces of OVS code in order to take this segmentation of memory into account. We have an example here that we've taken from the OVS user space tunneling, where you push and you pop headers, and in certain circumstances you then need to recalculate the checksums around the data, and the checksum function actually traverses the entire packet data according to the packet size, as if the data was contiguous in memory. And so since this is no longer the case when using the multi-segment MBUFs, this is an example of how we needed to rework this piece of code in order to take the segmentation of memory into account. And so with the addition of the multi-segment MBUFs, this is how our OvS-DPDK deployment would look like. So instead of the packet data being represented by a single MBUF, we would have the packet data being represented by a chain of MBUFs. And so now, if we want to integrate this with TSO, for each packet that we want to transmit, we need to tell DPDK not only that this packet is to be offloaded, but how to offload that packet. So we start by setting the L2, the L3, and the L4 length fields in the MBUF struct, so that this tells DPDK the size of each header in the packet. Then we set a few offloading flags. In this case, we tell DPDK that this is an IPv4 packet. We want DPDK to perform the checksum of the IP and TCP headers for us. And we also want DPDK to segment this packet for us. And we also tell DPDK the size of each segment, which is usually set to the MTU less the L3 and L4 header sizes. And finally, before we actually call the TX burst function in order to transmit the packets, we call the TX prepare. And this is actually a function that's available on newer versions of DPDK and makes our life a bit simpler because it abstracts operations that are done differently between devices, such as pre-calculating the checksum. And so going back to our previous discussion around the cost of running without TSO, now that we've had a TSO support, and so now that the operations of segmenting the data and performing the checksum calculations are being done in hardware instead of software, we should really now expect lower CPU loads and higher overall throughputs in our deployments. And that's actually what we've been getting during our tests. And so if we look to the graph on the left around the intra-host use case, you can see some considerable performance gains there. But this, as we discussed, this is actually expected, since in this use case, there is no need to segment the data or perform the checksum calculations on the data whatsoever. And so the performance difference between the deployment of OvS-DPDK without TSO and with TSO reflects exactly that. On the other hand, if we look at the inter-host use case, We see some more modest results, but we still see some considerable performance gains. We see around 70% performance gain when running OvS-DPDK with TSO. And this is expected as well, since in this use case, the data will need to be segmented anyway, and the checksum calculations will need to be performed. However, this is now being done by hardware and not software. And so that shows in these performance gains as well. And you can see that we start getting near line rate. So we start being bound by the physical network in this case. And so with this results in mind, there are a few considerations that we found while enabling this piece of work. And although most of them have to do with the multi-segment MBUFs, we have found, for example, that when enabling the multi-segment MBUFs, we lose the vectorized optimizations that are enabled by default in DPDK. But we also found that during our tests that this affects only the 64-byte sized packets. And since TSO is really aimed at larger sized packets, I don't think this should be a problem in this case. Then we also found that in newer versions of DPDK, the API to query for the offloading features of the devices is much better integrated. So it's easier for us to ask for TSO support on the several existing devices on a deployment compared to previous versions of DPDK. And then it's back to the point that we've mentioned already. So since we're using the multi-segment MBUFs, we actually needed to rework some parts of the code in OvS in order to take the segmentation of memory into account. And in other cases, actually, for example, when integrating in user space with the type interfaces, where fixed functions are being used that expect contiguous memory to be passed, we saw no other option other than using, other than actually copying the data from those multi-segment MBUFs and putting it in a contiguous region of memory and passing that instead. And the other point is that there's no GSO fallback yet, and so if we enable TSO and an interface doesn't actually support TSO, then when that packet is getting to the interface, we'll actually need to drop that packet, since otherwise the packet will get to the interface without any type of segmentation or any type of checksum calculations at all. And finally, with regards to the status of the work presented here, we're pretty much at the point where we have submitted upstream both of the pieces of work that we presented here. So the multi-segment MBUF patch set is really on its later stages, and the TSO work has been submitted under an RFC tag. And our focus at the moment is really on getting the multi-segment MBUFs work upstream, so we could then follow up with the rest of the TSO work. And finally, we are also pondering on adding GSO support, and this is mainly because we think it would lead to a better integration between all of the user spaces, the user space interfaces. Since if one doesn't support TSO, it could always fall back to GSO. And yeah, and that's all I have. Any questions?
Let's thank our speaker.
Thank you.
And we do have time for some questions. If you have a question, please come up to one of the mics.
I know some NICs can offload TCP as a TLE. So I don't think it's similar to TSO.
So TSO stands for TCP Segmentation Offload. Yeah.
I mean, some NICs can offload this by hardware.
Yeah.
But for this, it's DPDK software do, right?
Sorry, I don't get the question.
I think you're talking about NICs that have more advanced TCP offload. They have TOE, TCP offload engine support.
Yeah.
Oh, okay. Yeah, so our work here was mainly to get the first phases working. So the TSO is kind of an initial phase. We would then could consider adding support, but this would, at the level of the OvS and DPDK interactions, would be just kind of enabling a few flags, but we could then look at enabling, for example, supporting offloading, including VXLAN headers and VLAN headers as well. Was that the question?
Sorry. I know DPDK can do TSO and JSO, right? But
yeah.
It's done by software, not hardware, right? Actually, some NICs can do this by hardware. I mean, if you enable a TSO and JSO in OvS-DPDK, you can enable hardware to offload this work.
I think you did enable TSO hardware support, right?
Yeah, yeah. So
okay. Yeah.
Wait, let me try to go back. So here, in this case, what we're doing is actually telling DPDK that we want to offload the packets, and telling DPDK that these operations, like the segmentation of the packet and the checksum calculations, to be done by it and to be offloaded by DPDK.
Okay, thank you.
Does that, okay.
I think you answered this question.
Okay.
So I have a quick question.
Yeah.
So I was a little surprised to see the example of computing the IP checksum. I thought that the IP checksum just covered the IP header itself, and I would have expected that would all be within the first of those chained MBUFs.
So you're referring to that one at the top, right?
Well, you had something where you were adjusting how the IP checksum is calculated or recalculated because it might span more than one MBUF. But I would expect that the IP
yes,
the IP header is small and would always be in the first MBUF.
Yeah, so there are a few considerations around this. So on the work that we're trying to do, most of the work around the multi-segment MBUFs right now at the moment, because there were several iterations, but right now at the moment is actually trying to kind of make sure that all of the headers are on the first segment.
Okay.
So we won't actually have to kind of do the work of consider headers that span across MBUFs. But that's a good point, actually, yeah.
Okay. Let's thank our speaker one more time.